Hey everybody, it's Craig here. I'd like to talk to you guys about a very interesting experiment you can do with your solar cell before you assemble it in your product to measure the efficiencies at various light levels, color temperatures, and intensities and things like that. And it doesn't cost much to do this experiment. You take your solar cell, you'll need one of those, you'll need some spacers here, you'll need some kind of a little lamp, right, a hanging lamp, and I've got a special bulb in here. This is one of those LED bulbs that produce different colors using your phone. This particular one is from Wiz, W-I-Z, but there's lots of them out there. And we're just going to put that lamp right over top of the solar cell. We also have a little multimeter right here. This is a very inexpensive one. It costs about $5 to $10. Online, you can get them many places, with the ability to measure current and voltage. And I have taken my solar cell and I've hooked up the black lead to the negative side of the ammeter and the red lead to the positive side, and we're going to make some measurements here. Now, what we need to do is we need to make the measurements of the solar cell at various light conditions. So you can see right here, this is my application on my phone, and I can choose custom color right there. And using custom color, I can choose the brightest red I can possibly find. And then I can move it from red to yellow to green, all the way back until it circles around to red again. And we'll keep the intensity high as possible, although I can change the saturation as well. But we're going to keep it high so we get as much current and voltage as we possibly can. So as you go through the different colors in your phone, you're going to be making two very important measurements. The first measurement is going to be open circuit voltage. Now, open circuit voltage is basically you're hooked straight up to the voltmeter. You're measuring the voltage of the voltmeter without any load on the voltmeter at all, just the meter itself. So you can see that we're actually measuring a voltage here about 3.48 volts, and you'll record that voltage at this color, so blue about 3.48. At the same color, we're going to go over and measure the current that's being produced by this solar cell. And this solar cell at this light level is producing 0.7 milliamps. We're on the 20 milliamp scale, so it's doing about 0.7 milliamps. And we're going to make that for all the different color measurements we have available to us. We can also do measurements at different color temperatures. So if we move here, we can actually see we have the ability to change the color temperature on our solar cell to whatever we want it to be. So we can go from cool white all the way up to, keep the intensity as high as possible, all the way up to, all the way down to warm white. So there's 2200 K, which is a warm, and it's climbing up to 3200 and so on until we get to 5600 cool white. And we can go ahead and measure the current and the voltage at each one of those temperatures and put it into our table. Now, once we've done all that, we're going to do a little bit of analysis on that. So if you look over here, this is a spreadsheet that I've put together, and you can see all the different colors that I'm interested in, from red to orange all the way up to violet. And this column here holds the wavelengths of those different colors. So the distance from peak to peak of a red is 650 nanometers, and that goes all the way to 400 nanometers for violet. So it's a much shorter distance peak to peak for violet because it's a higher frequency. The next column does show us frequencies, so we can see that the red is 4.62 times 10 to the 14th cycles per second, or hertz, and that goes all the way up to 7.5 times 10 to the 14th hertz. So that's most of our visible range right here. The column I put beside that is the energy in electron volts produced by the solar cells, by the light, I should say. So 1.91 electron volts for red, but it goes all the way up to the highest energy photons, 3.1 electron volts for violet. Okay, now these are the two columns I want you to calculate. I want you to measure the open circuit voltage at each of these different colors and the short circuit current. So the voltage, you see, starts at 5 volts for red, in my case, and goes up to about 5.13. The short circuit current goes from 0.46 milliamps all the way up to 0.528. Now, it's very interesting to see the voltage change a little bit and the current dramatically change. Of course, more current's being produced because solar cells ultimately are a current generating device. Now you can take the voltage and the current and figure out the power. Power is equal to current times voltage. So this column here is simply current times voltage. Now, and we can actually, I'll just add this extra piece on right here. So you can see that in red, the power is about 2.34 milliwatts for the solar cell. Blue goes all the way up to 2.98 milliwatts, so it really tends to peak around blue. And then violet, in this case, drops to about 2.71. So there's a little bit of an intensity drop. So there's the power. Now it's interesting to take the current and the voltage you see right here, and we can plot them. So we can see the frequency along the bottom of this open circuit voltage chart and the short circuit current part right here. And you can see it actually peaks out at about 450 nanometers for the open circuit voltage, peaks out around 450 nanometers for the short circuit, which is around blue. And of course, those two would have the highest power as well. So that's where we're getting the most power. And there you can see this is from the actual manufacturer of the solar cell. This is an amorphous silicon solar cell, which is this purple line right here. So you can see there is a very narrow range, which it is very, very sensitive to light. And other solar cells with other materials can have different performances. Now, I've also continued down here to look at how white affects the solar cell. So here you can see in column 12, or row 12, we have the white light, which is produced 5.74 volts, 4.04 milliamps, and a lot of power, 23.19 milliwatts of power. Daylight was 5.64 and 3.54, so it produced about 19.97, and cool white produced about 21.17. Below that, I used my phone's Wiz application to control the color temperature of the little bulb, and I went from 2200K all the way to 6200K. 6200K being a bright white, almost like a snowy, sunny day. And you can see again the power really peaks with the higher color temperatures, up to 20.2. So I encourage you to go ahead and take your solar cell and make those metrics on your cell to find out just what makes it perform best. You can also try experiments by putting things in front of the solar cell, like a plastic sheet or a glass sheet, or different kinds of windows, to see if the fact that those windows are blocking some of the higher frequency lights or maybe the lower frequency lights, how much it diminishes the efficiency of your solar cell. So have fun with your solar cell and learn a lot more about solar harvesting by doing these very simple experiments.